Greetings of the day. I'm Ramya from PS University Bengaluru, presenting you the paper titled A Comparative Analysis of Constant Impedance and Constant Power Loads in a Distribution Network, which has been accepted for publication in International Journal of Electrical and Computer Engineering. The authors of this paper are Ms. Ramya and Dr. Rex Joseph from Department of Electrical and Electronics Engineering, PS University Bengaluru. I would like to start the by explaining the motivation of this paper. In the traditional power system, the loads are of CIL type, that is constant impedance load type. With large-scale influx of electrical vehicles and tightly fed power electronic converters, they behave like constant power loads which alter the characteristics of traditional power systems. Constant power loads have higher transmission losses and reduced stability. To increase the reliability and to reduce transmission losses, distributed energy resources such as solar PV and wind energy resources are integrated, giving scope for peer-to-peer energy sharing between the consumers. Even though total transmission loss in distribution systems are only 4 to 5% of generation, this would be significant when there would be multiple energy transactions. Hence, allocation of transmission losses, optimization of energy scheduling, considering energy availability, distance, etc. becomes prominent in increasing energy efficiency and profitability of the consumer. To start with the analysis, we have considered a radial type of distribution network wherein we have a AC voltage source which is of 230 volt and 50 Hz. We have multiple loads which can be constant impedance type or else constant power load type. And the transmission lines we have considered a short transmission line model which has only resistance and inductance with it. And the nodes can be node 1, node 2 and it can go up to node n. In the graph here we have considered x-axis as nodes and on the y-axis we have load voltage and line current. If you observe, we can see the maximum load voltage and the line current is wherever the generation are. And as we move away from the generation, the load voltage and line current keeps on decreasing. In the second case, we have added one more additional AC generating source at the end of the distribution network, that is at the receiving end. We can observe that wherever the AC voltage source, the load voltage and line current is the maximum. And as we move away from the generation, the load voltage and line current keeps on decreasing. The graph here shows the characteristics of constant power loads. We have current on the x-axis, voltage on the y-axis. We can see here as the voltage keeps on increasing, the current keeps on decreasing. Even though the voltage by current ratio is positive, the delta change of voltage divided by the delta change of current, delta V by delta I, is always negative. That is, the incremental impedance of the constant power loads is always negative. That's why the system is highly unstable. The figure shows the mathematical model of constant power loads. We have used Kirchhoff's voltage law, Kirchhoff's current law, and a PI controller to implement this mathematical model. The table shows the parameters which we have used for further simulation and the current mathematical modeling. The sending end voltage to be 230 volt and 50 Hz, consumer load as 3 kilowatt, transmission line its resistance is 0.02 ohm and its inductance as 40 microhenry, so as it is a short transmission line. Kp and Ki values for a PI controller as 0.00005 and 0.01 respectively. The mathematical model has been simulated and verified here. In figure 5, we have used a load type of constant impedance load, and at 0.3 seconds we have increased our source voltage so that the load voltage at that node will increase. Similarly, due to which the line current will also increasing, which increases the load power in return. Whereas if we use constant power load type, as we increase our load voltage, the line current will decrease so that the load power will maintain constant whether we increase or decrease the load voltage. Next, we have considered standard IEEE 31 bus 23 kV distribution system. Here as a source we have a distribution transformer which is at 415 volt and there are 53 consumers. These consumers can be mostly residential loads So R2 to R53 are residential loads, which are basically constant impedance load type. And we have considered in the later cases, we have added 50% of the consumers, that is 26 loads, to have PEV chargers, which are constant power load types. Constant impedance load, we have considered it to have a power of 1500 watt at unity power factor, and constant power loads, we have assumed it to be 4000 watt. The figure shows voltage profile of all consumers. On the x-axis, we have different loads representing consumers. On the y-axis, we have voltage profile, which is represented in per unit. In case 1, we have considered all to be only residential loads, which are constant impedance loads. As we can see in the figure, standard voltage limit of 0.9 per unit has been crossed at 2 points as the distribution system is radial in structure. In the second case, we have added 26 PEV chargers to random residential loads, which caused voltage to cross beyond standard voltage limit at 4 places. So the voltage violation is more frequent and can get adverse with more loads on it. As mentioned before, adding distributed energy resources and having local energy sharing arrangements will significantly improve the voltage profile. So we have added 4 DER additional DERs in the system. Improvement in the voltage profile has been observed here. As transmission losses are significant in distribution system with constant power loads having local sharing arrangements, loss allocation between loads and generators is necessary. This has been implemented using Bialec's method of electricity tracing using upstream looking algorithm. Mathematical equations used for the same has been given below. The results show that transmission losses of consumers near generators or DERs are comparatively less than the consumers which are not. In the figure and table, we can observe that transmission losses are higher with the constant power loads than constant impedance loads. And by the additional DERs, transmission losses have been reduced from 5.3413% to 1.9049%. So, in conclusion, it is observed that constant power loads lead to higher voltage drops and losses compared to constant impedance loads. It also affects the system dynamics and could potentially lead the system to instability. The dynamic model developed can be used to study the effects of load dynamics, which can be altered to make the individual loads. Energy sharing between the customers helps to avoid voltage drop and minimize transmission power loss in radial distribution network. Consumers who have renewable energy or battery storage may become producer based on their energy availability. This would also greatly enhance the power handling capacity of the network. In certain transmission lines, energy sharing results in greater energy transmission than in others. In the prosumer model, computation and allocation of losses is important for matching energy and build usage. As a result, allocation of the losses becomes crucial to the billing process. So, this analysis which has been done can be extended to optimize and cost energy transfer between the peers.